All right, sigma notation. Hopefully you have seen this symbol. If you've done any type of spreadsheets, this symbol in a spreadsheet means summation. So if you're in a spreadsheet and you have a list of numbers, you can go to the cell at the bottom of those numbers and you can click this button and it'll add up the cells. It's backwards. So this symbol means summation. It's the Greek letter symbol. It's sigma. It is uppercase sigma, and it means add it all up. That's literally what it means. So this particular one says the sum of the n terms a sub 1, a sub 2, a sub 3 to a sub n is written like this. Those little sub numbers just tell you what term they're talking about, the first term, the second term, the third term, and so on and so forth. I, down here you see the I. It's the index of the summation. It's where you start. And then up here is where you end. That's how many terms you're going to have. So the upper and lower bounds of the summation are 1 and n. And they give some examples. So let's say I have the summation of I from 1 to 6. It literally means 1 plus 2 plus 3 plus 4 plus 5 plus 6. The summation here of I plus 1 starting at 0, well, you plug it in. 0 plus 1, 1. 1 plus 1, 2 is my second term. All the way up to 5 plus 1, 6. You can do really anything. J squared, and they just squared from 3 to 7 and added them up. 1 over n, k squared plus 1. The n is not filled in because it is an n, by the way, but this is just telling you this is a summation that you don't know how many terms you have. Same thing here, a function of x, delta x, that's change in x. And so we're just doing the function of x of 1, x of 2, x of 3. And so again, this is a variable thrown into it. So there's different ways that you can do summations. And then there are certain ones that are known. So certain summations you know what you're going to do with. Other ones you just follow the pattern of whatever it tells you to do. And so we are going to look at a set of known summations. All right. These are some summation formulas that always have this repeated pattern. The first one is just a constant. A constant from 1 to n is just going to be that constant times your n. Because basically if it's a constant, you're saying the constant plus the constant plus the constant, that is your term. And you're going to do it however many times it tells you, n times. So you end up just multiplying the constant times n. Like this first one where it's like 1 plus 2 plus 3 plus 4 plus 5. This is a known summation. If you're just adding up numbers from 1 to a certain number, this is always going to be what you do. It's going to be the number of terms you have plus the number of terms plus 1 divided by 2. This is actually also Gauss's formula, if you remember the story of Gauss. And his teacher told him to add up the numbers 1 to 100, and he was able to do it quickly. This is how this formula is. So you would say 100 plus 101 divided by 2, and you would get that 5,050 are the numbers from 1 to 100. And so just adding up integers from 1 to something is this formula right here. You're going to do your top, however many terms you have, times that plus 1 divided by 2. The next one that is known is I squared. So let's say you're doing a sum of the squares. 1 squared plus 2 squared plus 3 squared plus 4 squared up to 100 squared. Yeah, you could do it. That's a fun way to do it. Or it's always going to be however many terms you have. If we have 100 plus 101 plus 201 divided by 6. It's always going to add up to that. And then cubed. Again, sum of the cubes. You could do 1 cubed plus 2 cubed plus 3 cubed. That's great if you have 3 terms. It's not great if you have 50. And so instead of adding up cubes, you can just say how many am I going to end up with? Squared, n plus 1 squared over 4. I will say these two look very much alike. Your I and your I cubed look very much alike to me, right? They just squared everything. So if you can remember, the I and the I cubed are similar, and this guy is his own little monster right there. So they want us to evaluate I plus 1 over n squared. N squared is just a number, okay? So I is what we're actually adding. We're adding the 1 plus the 2 plus the 3 plus the 4 and so on and so forth. And so when you have something like this, do the summation and pull the constant out. By that I mean, this is the same thing as saying 1 over n squared times I plus 1, right? And so I can actually put that n squared on the outside here, 1 over n squared, summation of I equals 1 to n of I plus 1. When I have summations, I can do them individually. So this right here is the summation of I, and this right here is the summation of a constant. That's not a pretty summation sign. There we go. Of a constant, which is 1. All right. So I can go back to my formulas and I can say, well, what was my summation for I? What was that formula? And what was my summation for just a constant? All right. So for I can replace this with n times n plus 1 over 2. And I can replace this with just my constant, which is 1 times n. Right? And you can simplify this. This is all being multiplied by 1 over n squared. All right? So simplify it, 1 over n squared. Distribute this guy, n squared plus n over 2 plus n. We can say, yeah, that's fine. Distribute this guy through, right? Distribute him through. 1 n cancels, so 1 over n squared. If I had n squared plus n over 2n squared, which is what's going to happen when I distribute this, plus n over n squared, you can see I can simplify those, right? So I can take an n out. 1 n here, 1 n here, 1 n here. So I have n plus 1 over 2n. And then an n cancels here, plus 1 over n. Try to make it as simple as possible because they want me to do it for 10, 100, 1,000, and 10,000. So the more simple you can get it, the easier it is to plug it in. So I would actually do a common denominator here. 2n and n has a common denominator of 2n, so multiply top and bottom by 2, right? So now I have a common denominator, n plus 1 plus 2 over 2n, or n plus 3 over 2n, all right? So here's what I'm doing. I'm simplifying it by plugging in my summations for my I and my constant. After that, it is just algebra. You are literally distributing, combining like terms, getting common denominators until you get this very simple n plus 3 over 2n, all right? Now, they want to know it for the first 10 elements, the first 100 elements, the first 1,000, and the first 10,000. Now I can just plug those in. I can plug a 10 in. 10 plus 3 over 2 times 10, right? I can plug in a 10,000 if I want to. 10,000 plus 3 over 2 times 10,000, all right? And they give you the decimals here. This guy is like approximately 0.65. This guy is approximately 0.50. All right. What does that tell me? That tells me if I were to put 1 plus 1 over 10 squared, plus 2 plus 1 over 10 squared, plus 3 plus 1 over 10 squared, plus 4 all the way up to 10, I would get 0.65. If I were to do it to 10,000, 1 plus 1 over 10,000 squared, plus 2 plus 1 over 10,000 squared, plus 3 plus 1 over 10,000 squared, all the way up to 10,000, I would get 0.5. I would much rather simplify this guy right here to look like this, where I can just plug in the term that I want, than actually sit there and add up those terms, right? And so that's what this does. Summations help you simplify these so that you can figure out what the first terms are without having to write them out. So one thing we talked about really at the beginning of the year is pre-calculus versus calculus, right? Pre-calculus world, we're given a rectangle and we're told to find area. And it is stagnant. By stagnant, I mean that formula never changes for a rectangle. If you have a rectangle, it will always be base times height, length times width, whatever, right? Circle. We have a perfect formula for the area of a circle. There's no question. We don't have to try to figure it out. But when you get into the calculus world, you get into shapes that are not known. If I want the area under this curve, there is not a known formula in pre-cal to give me that shape. A shape that has two straight sides here, a third little short one, and then a curve. There's not a name for that. It's not a polygon, right? And so we start by saying, well, let's use the known to figure out the unknown, right? The known here would be rectangles. If I have these rectangles, these 5 rectangles, then I can say, well, I could calculate those 5 rectangles, and that would be close to the area. But you can see that I will be lacking in some of this. This little pink area here, I didn't actually get that area in my estimation. So then that is the left side. So if I use the left-hand side and say, okay, what is my base here is 0 to 2/5, right? That's my base. My height is whatever happens when I plug in a 0 for this function. 0 squared plus 5, my height is 5. So 2/5 times 5, that area, and I'm doing it 2/5 apart. So what I did was I took all of this and divided it into 5s, all right? And then another 2/5 here is my base, and then whatever happens when I plug in this side of it and get that height, right? And same thing here, base times height, and I just add up the 5 rectangles. If I do it the other way, let's say I do the right-hand side and I do these 5, I'm actually going to be a little bit above my area because you can see that I've got some pieces that are sticking out above what I actually want. This is called approximation because it's not exact, right? And so really the more rectangles you have, the closer you're going to get. But typically they will tell you, hey, use this number of rectangles. And instead of doing your rectangle formula so many times, you're going to use your summation to try to do it so that you don't have to do this over and over and over and over. All right, so it says use the 5 rectangles in the figure to find 2 approximations of the area of the region. All right? And so it tells you these endpoints here. The endpoints here are 0 to 2/5, 2/5 to 4/5, 4/5 to 6/5, 6/5 to 8/5, and 8/5 to 10/5. All right? And so this is my evaluation here if I were to evaluate it on the right-hand side, right? So now we're going to have to look at what my height is versus what my width is. My width is always going to be 2/5, right? You can see that. I went from 0 to 2. So on the coordinate plane, this is 0, this is 2, right? And I split it into 5, all right? So it's going to be 2/5 each. So if I'm talking about my base here, my base, the width is always going to be 2/5. What's my height? Well, my height is my y value. How do I find my y value? Well, I plug it into my function, right? Except it's changing. So my first y value is 2/5, my second is 4/5, my third is 6/5, 8/5, 10/5, right? And I don't want to do it that many times. So how do I figure it out? Well, this is 2/5 times 1. This is 2/5 times 2, times 3, times 4, times 5, right? So I'm actually multiplying by 1, 2, 3, 4, 5. I'm going up by 1, all right? So if I take 2/5 and multiply by whichever term I'm on and plug it into my function, I will get my y value. All right?
So you don't need the 2/5, you just need the 2i/5.
It's both. So this is my height and this is my width. Okay? So my width is stagnant, right? My width is always 2/5. My height changes depending on which element I am at. If I'm at the first element, it's going to be 2/5 times 1. The second one is going to be 2/5 times 2. The third one, so I'm using I because I'm walking by 1. 1, 2, 3, 4, 5. If I was walking by I squared, by squares, I would do I squared, right? But I'm walking by ones. And so I'm going to put an I there, which means I can add up, there's a summation formula, starting at 1, right? And how many rectangles do I have? Well, I have 5, going up to 5. So this is going to be a summation formula, all right? Now, when I do this, f of this means I need to plug it in. F of 1 would be negative 1 squared plus 5. F of 2 would be negative 2 squared plus 5. F of a would be negative a squared plus 5. F of 2i over 5 is negative 2i over 5 squared plus 5, right? And so I'm going to replace this piece of it with what happens when I plug it in. So negative 2i over 5 squared plus 5, right? That's what happens when I plug it into the function. That gives me my y value, okay? Times my width, which is stagnant. The width does not change. It's always 2/5. And I still want my summation from my first term to my 5th term, okay? And now I need to simplify this guy. I need to make sure that I have really everything as simple as possible so I can replace my constants with my constant and with my I squared summation. All right, so that's what I'm going to do. I'm going to scoot this up so I don't run out of room. All right, I'm really going to just do algebra in here. What happens when I square 2i squared? I over 5 squared, I have a 4, an I squared, and a 5 squared, which is 25, and that's negative, plus 5, multiplied by 2/5, all right? I'm going to distribute that 2/5 through, right? So when I distribute this 2/5 here, I get negative 8 I squared over 125, plus this just becomes 2, right? Okay. And I'm still doing a summation. All right. So when I do a summation here, that negative 8 over 125, I can just pull out, right? And I can do my summation for I squared. So I can say negative 8 over 125 times what's my I squared summation. So we're going to go back to our summations and we're going to look at our I squared. Our I squared is n times n plus 1 times 2n plus 1 over 6, right? And then my summation for this guy is just 2 times n, right? Now here's the thing. If you're only doing one guy, and unless I ask for the simplified version of this, you can literally plug in your 5 if you want to and just do your calculations. Does that make sense? So you could simplify all this if you want to, or you could plug a 5 in for every n. So this is going to become 5, this is going to be 6, and this is going to be 11. 5 times 6 times 11. Does everybody see that? And then just simplify. So like these guys will cancel. So you have 55 times negative 8 over 125 plus 2 times 5 plus 10. And when you do all of that, they give us the answer here. We can do it out. It's going to be a decimal, 6.48. All right. 6.48. That is my approximation of what that area is. So you're always going to use however far you go. So they'll say go from 0 to 2 and use 5 rectangles, okay? Which means you're going to say, all right, I need to subtract these 2, right? How wide is it? Divided by how many rectangles I'm going to have, okay? That will always be my width, period. This will always be my width. Subtract your distance from start to finish, divide by how many rectangles you have, all right? This will be my width. You're going to take that width and you're going to just multiply it by I and plug it into your function. So multiply your width times your I and plug it into your function. That is going to be your height. Then you're going to simplify it, use your summations, however you need to use them, and then plug in how many rectangles you have to get your actual area. All right. Common sense here is the area of the region, if you do below it, above it, it's going to actually be in between them. That's all this is saying. That the actual area is going to be in between your lower end and your upper end that you estimate on, which makes sense, right? If you go below the line a little bit, above the line a little bit, the actual area would have to be in between them. And that's all this is telling you. You're bounded by the region. They give us this function here, f of x equals x squared, between 0 and 2. Between 0 and 2. And we are going to use 5 rectangles here as well. Okay? And actually, I think they want us to do it without using a specific number. They used 5, but we're going to just use n, okay? So I'm going to subtract the 2. 2 minus 0 divided by the number of rectangles, all right? So my width here is going to be 2 over n, all right? My height is going to be the function when you plug in 2I over n. Just take your width, multiply by I. All right? So that means my height, I've got to plug it in here. If I plug this in, it's going to be, instead of x squared, 2I over n squared, which is going to look like this, 4I squared over n squared, right? So I have my height and I have my width. Okay? So far, so good? My summation, if they don't tell me a number, then I'm just going to go from 1 to n. It will all work out. Of my height, 4I squared over n squared times my width, 2 over n. Height times width. That's how you find the area of a rectangle. Simplify this first. How does this simplify? Well, 4I squared times 2 is 8I squared. N squared times n is n cubed. Okay? N cubed is just a number. So we're going to pull that out in front along with that 8. Okay? 8 is just a number. N cubed is just a number. They just didn't tell me. Last time they said 5. This time they didn't tell me. So I'm just going to leave it. So I'm just going to pull the 8 over n cubed out here. And I need the summation then of just I squared. So I'm going to go back to my summation formulas. And I'm going to say, what's my summation of I squared? That's your n plus 1, 2n plus 1, right? n plus 1, 2n plus 1 over 6. So we're just replacing that I squared with this guy here. Now, when they don't give you numbers, you need to simplify him, okay? Because at the end they could say, now do it for 5 rectangles. Nope, now do it for 10 rectangles. Nope, now do it for 20 rectangles, okay? So instead of doing it 15 times, however many times they ask for it, we're going to simplify this guy. He simplifies nicely. I will tell you that. All right. So when you do this, you want to distribute these. Okay. So I usually just FOIL these two. So I have like 2n squared. This is 2n and 1n. So this is going to be 3n plus 1, right? And then I need to distribute this n to all of them. So it becomes 2n cubed plus 3n squared plus 1n. Everybody see what I did? I just FOILed it and then distributed that n over 6, right? And I'm multiplying this guy by 1 over n cubed, all right? I'm going to obviously simplify my 8 and my 6, right? Clearly I want to do that because it does simplify. So I'm going to simplify these guys, just cross cancel them just like you would. What goes into both of them? 2, right? So those become 3 and 4. And then I'm going to split them up, okay? So I'm going to say 4 times 2n cubed. That's 8n cubed over 3n cubed is going to be my denominator for all of these, okay? 4 times this guy. This is going to be 12n squared over 3n cubed, right? And then distribute here. This is going to be 4n over 3n cubed. So that's what I'm going to do here so I can simplify them individually, okay? And so the n's here cancel completely, so I get 8 thirds. 2 of the n's cancel. and the 3 reduces, so I get 4 over n. And then one of my n's cancel, and I get 4 over 3n squared. Okay? 4 over 3n squared. Now, how does this help me? Well, what you're going to find is, let's say I had 10 rectangles. What would I do here? I'd plug a 10 in, right?
I found this on the web.
No, I don't want your help. So if they said 10 rectangles, you would say, okay, I'm going to plug a 10 in here and a 10 in here, and I'm going to estimate it. Yes? Would I be closer to the actual area if I said 100? Well, clearly I would be closer, right? So plug in 100. Well, I'm going to plug in 100 here and 100 here, right? Plug in 1,000. Well, I'm going to plug in 1,000 here and 1,000 here. But let's say I want to get really close. Do I know how to do these limits? Yeah, I know how to do these limits. The limit of a constant doesn't change. What's the limit at the 8/3? Well, it's just going to be 8/3. What about here? I'm going to use my shortcuts. Where's my degree? Yeah. What about here? There we go. And so I can use limit theory with my summation to get my area. My area here is 8/3. Okay. And that's my actual area. All right. So when you use limit theory, you're not approximating anymore. You are actually getting to your area. So this is the actual definition. The definition of the area region is going to be the limit as n approaches infinity of your summation, function of what you put in here. This is what we just did when we subtracted and divided by n. Change in x, well, that is my subtraction divided by n. Okay? And so this is just the formula that we just did, but this is saying the limit theory is going to actually equal that area. When you do infinite number of rectangles, now you've actually moved to the actual area under the curve. Find the area of the region bounded by the graph of x equals x cubed. That gives me my function. The x-axis and the lines 0 to 1. All right, so they've given us our width down here, 0 to 1. So to find my width, we're going to say 1 minus 0, 1 over n. My height then is going to be what happens when I plug that times I into my function. Specifically, my function is x cubed. So my height is going to be I cubed over n cubed. All right. So I'm going to take that and do my summation. So my limit theory says take the limit as n approaches infinity. Summation of this height, I cubed over n cubed, times this width, 1 over n. Okay? I end up with I cubed over n to the 4th, but I can pull that 1 over n to the 4th completely out, right? So I can say 1 over n to the 4th goes here, and just do the summation then of the I cubed. Summation of I cubed looks actually just like I, it's just everything is squared. So it's n squared over n plus 1 squared over 4, right? Times 1 over n to the 4th. All right. Simplify it. When I FOIL this guy out, I get n squared plus 2n plus 1, and then distribute this n squared. So that becomes n to the 4th, 2n squared, 2n cubed, there we go, and 1n squared, all over 4n to the 4th, right? So far, so good? Now here's the thing. I can split them up if I want to. Or I can just use my limit theory right here, can't I? Yeah? Limit theory as n approaches infinity of n to the 4th plus 2n cubed plus n squared over 4n to the 4th. What do I know about my degrees? They're the same. I'm going to use my coefficients. My area here is going to be 1/4. That's my answer.